Hi, this is the middle fifth end of year paper review, section B for double award. So the first thing here is which one of the three particles in an atom is negative, and it's an electron, which is the smallest mass, and an electron again. So that sometimes unnerves people, and they think the answers have to change. Okay, atoms are neutral because they contain equal numbers of protons and electrons. Okay, could be electrons and protons, doesn't matter, but it's those two particles together. Isotopes of an atom have the same number. Now we're talking about subatomic particles. They have the same number of protons, but different numbers of neutrons. It has to be about the subatomic particles. This is stuff we would have done in the lower fifth. Okay, so here we are. And we would have revised it again. So the next thing we need to work out here is the atomic number of protons is 12. The mass number is 24, and the electronic configuration, there's 12 electrons, so it's 281. Oh, just ignore that. Okay, so where are we now? So we're adding barium chloride to sodium sulfate. Now it makes barium sulfate, and barium sulfate, you should know, is insoluble. Okay, it's one of those insoluble ions that you need to know. So that's testing your knowledge of solubility of ions. So it's a white precipitate, a white solid. That's 1 mark. Next one is potassium chloride plus sodium carbonate. So it's going to be potassium carbonate and sodium chloride, both group 1. So all group 1 salts are soluble. So you're not going to see any change. There's going to be no changes. There's going to be two colourless solutions forming a colourless solution, two colourless solutions rather. Next one is calcium chloride plus sodium sulfate. You're going to make calcium sulfate, which is another insoluble sulfate. And it's white, so you're going to see a white precipitate or a white solid forming. That's just learning your solubility rules. Okay, when a solution of lead nitrate and potassium bromide are mixed, a precipitate of lead bromide, so if it's a precipitate, it's a solid, and a solution of potassium nitrate are produced. So it's just putting those informations. The two solutions at the beginning, so they're both AQ because they're solutions. The next one is a solid, a precipitate, so lead bromide is solid, and a solution of potassium nitrate. So it's just reading the question. Okay, in order to prepare a dry sample of lead bromide, student took the mixture, filtered the mixture, washed it. Okay, so why do they need to filter the mixture? Well, they want to collect the solid of lead bromide, or they might want to remove the solution. That's effectively all they're asking you there. That's why do we filter things? To separate a solid from a solution, or solid from a liquid. So something sensible along those lines. 1 mark. Why did he wash the solid residue? To remove any impurities that might still be on the lead bromide. So what impurities might they be? Well, it might be the potassium salt, which was the potassium nitrate salt. So there could be a very, very fine amount still on it, but it still could contaminate your results. That's why you need to wash it. Why is it better to use distilled water? Well, distilled water has no impurities in it, so something about no impurities in there. There's no dissolved ions in distilled water. So something about the purity of it. Why was it left in a warm place? Well, you want to dry it because you want to evaporate off the water. Remember, it's been washed with distilled water, so it's the water you want to drive off. So here we are. We've got something dissolving here over 2 days. So which one explains this observation? Well, the first one here is the crystals dissolve. Next one, let's go on to A. The 2 weeks the crystal has disappeared. Describe the appearance of the liquid of the beaker after 2 weeks. Well, it's all blue now because of diffusion. Okay, so the next one, the formula of compound crystal is CuSO4.5H2O. How many different elements? There are 4: copper, sulfur, oxygen, and hydrogen. How many different atoms? Well, there's 1 copper, 1 sulfur, 4 oxygens, then 5 times 2 hydrogens, and then 5 times 1 oxygen again. So if you add those up, that should equal 21. Trickier question than it at first appears. So next one here, the question is about the elements in group 1. Group 1 elements are metals, so therefore they're going to be good electrical conductors, and also metal oxides are bases. So it's going to be C, good electrical conductor, and it forms a base. So a bit of knowledge on group 1 metals and metal pHs, metal oxide pHs. State 2 observations that could be made. Well, it's going to produce hydrogen, so you're not going to see hydrogen being produced, but you will see fizzing, bubbling, or the correct word is effervescence. But you can't say you're going to see hydrogen. You don't see hydrogen, you have to test for hydrogen, but you do see fizzing or bubbling. That's what you would observe. And what would you see of the sodium? Well, the sodium's going to be moving around. It will be melting into a ball. It's floating on the surface. It will gradually disappear as it dissolves. So you'll see it disappear or get smaller. Yes, okay, you might see it form into a ball as it melts. It melts into a ball, gets smaller. So all these are all the different things, but they're all grouped together. I've written all over the next question. Potassium reacts in a similar way to sodium, but is more reactive. State 1 observation that could be made when a small piece of potassium is added to a large trough of water. Well, the one thing you definitely see is you can see it auto ignites the hydrogen, so the hydrogen burns to give a lilac flame. So it's reacting because it's much more vigorous, the reaction. It's hotter, and so you're going to see a lilac flame as the hydrogen ignites, and sometimes it will even explode. So either of those will do. Next question, explain why the elements in group 1 have similar reactions. Well, all the elements in group 1 have 1 electron in their outer shell, so that's why they have the same or similar chemical reactions. So it's 1 electron in the outer shell. Right, lithium is an element of group 1. Lithium is stored in oil to prevent it coming into contact with water and air. When you take it out, remember the demonstration, it tarnishes, doesn't it? It goes dull in air once you cut it. Now, when you add it to water, you add a few drops of phenolphthalein. Phenolphthalein turns pink. That means it's testing for an alkali. That means that change from colourless to pink means that it's the appearance of an alkali there. Now, what is the alkali? Well, you've made lithium hydroxide, which has got hydroxide ions. That shows that it's an alkali. So if you put something down there of lithium hydroxide forms or hydroxide ion forms, okay. And then the next thing is saying that it's an alkali. So the solution is alkaline. Right, next one here. Lithium oxide. They give you lithium and they give you the oxide ion. Well, you remember if it forms a salt, or if it forms a compound that wants to be neutral, so you're going to need 2 lithiums for every 1 oxygen. So it's going to have to be Li2O. To make it neutral. Here you've got, now you know that lithium is +1, so therefore carbonate, which is CO3, must be 2- or -2 to counteract that. Don't worry about that line there. Right, last one here. In one experiment, so you've got 0.5 moles of magnesium carbonate and you've got 0.08 moles of hydrochloric acid. The key here is to use the ratio in the equation. Okay, so let's just put down a key bit of information. Show by calculating the moles that magnesium carbonate is in excess. Right, so if you've got 0.08 moles of hydrochloric acid and the ratio is 2:1, that means you're going to need half of that of magnesium carbonate. So you're only going to need 0.04 moles of magnesium carbonate, but you've got 0.5 moles, so it must be 0.05 moles. So you've got in excess of it. That's essentially what they're trying to show you. So let's just expand upon that. So 0.08 moles of HCl only requires 0.04 moles of magnesium carbonate. Why? Well, it's to do with the ratio from the equation. Magnesium carbonate to HCl from the equation is a 2:1 or 1:2, which way you're underwriting it. And so therefore you've got more moles of magnesium carbonate than you need for the reaction, so it's in excess. So one mark for explaining the ratios of what's needed, and 1 mark to say that you've got more magnesium carbonate than you need. Right, next one here is percentage yield. It says here you've got 0.05 moles of magnesium carbonate reacts with excess hydrochloric acid. And you get 5.5 grams of magnesium chloride. So therefore, you would expect that if you had 0.05 moles of magnesium carbonate, you would have 0.05 moles of magnesium chloride crystals forming, because it's a 1:1 ratio from the equation above. Now, you can work out the mass of the magnesium chloride crystals. First thing you need to work out is the MR of that. So here's your actual mass. Percentage yield is your actual mass over your theoretical mass times by 100. So your theoretical mass can be found out from 0.05 times by, it's Mr. moles, isn't it? So 203 times by 5, 0.05, sorry, times by 100. Bash this out on the calculator. What's 0.05 times by 203? That's 10.15 grams times by 100. Now that's a bit of a mess. Okay, it looks a bit messy there. Let's simplify it a little bit. So what you've got is your actual mass, which is 5.5 grams. You're expecting 10.15 grams. So it's 5.5 over 10.15 times by 100, which should give you about 54%. Okay, a little bit long-winded the first bit, but that's essentially what you're looking for. 1 mark for the 203, and 1 mark for the 54. Right, percentage yield might not be there. Well, magnesium carbonate might not be pure. You might not have transferred all of the crystals. Those are the most common mistakes there. Or also, I suppose you might not have left the magnesium chloride long enough to react, or you might not have left it long enough for crystals to form. Okay.